This video is going to cover 7.1 for statistics. We're going to talk about the normal distribution. So to start, a uniform distribution means all options are equally likely. So uniform, equally likely. So uniform is telling us that they're all the same. One uniform, you wear the same clothes. A probability density function, that's just what the PDF stands for when we did like the binom PDF. It's talking about the area under the curve as being your probability. The height is your probability, and then the density function is you're finding that area, and that's telling you the probability of what's going on. So let's look at an example of a uniform curve. Imagine the friend of yours is always late. Let the random variable x represent the time from when you're supposed to meet your friend until he shows up. So if your friend could be on time, x equals 0 for 0 minutes, or up to 30 minutes late, x equals 30. With all intervals of equal time in between 0 and 30 being equally likely. For example, your friend is just as likely to be 3 to 4 minutes late as he is to be 25 to 26 minutes late. The random variable x can be any value in the interval from 0 to 30. So if we were to draw a graph, it would look like this, from 0 to 30. And then each bar would be 1/30th, because that's the probability. So if I broke it down, just to kind of see where that goes, then within here we'd have 5, 15, 25, and then so we'd have essentially a bar graph with 40 bars all the same height. So our probability is the area. So if we're looking at the area of one bar, the width is 1 because it's 1 minute. 1 times 1/30th, the area gives us the probability. So now let's use that. What is the probability that your friend is more than 18 minutes late? So we know it's between 18 and 30, so we're going to subtract. 30 minus 18 gives us 12. So there's 12 blocks in the section we're talking about. So that means we're starting at 18 and we're going up here and we have 12 blocks. So we do the area, 12 blocks times the height of each block, which is 1 over 30, and we would get 0.4. So there's a 40% probability that our friend will be more than 18 minutes late. Now let's look at, I don't know what I'm doing. Never mind. The probability that your friend is between 10 and 20 minutes late. So because they're all the same, we're doing between 10 and 20. So 20 minus 10 is 10 blocks. And then we do 10 times 1/30th, and we get 0.33 or 33%. So 33% chance they'll be between 10 and 20 minutes late, which makes sense. That's a third of the block. All right, now we're going to work the other way. It's 10 a.m. There's a 20% probability that your friend will arrive within the next how many minutes? So we're doing that area equation where our base is the number of minutes. The height is the probability, which is 1/30th. And then the area is that 20% that we want. So our base is what we're looking for. The height is 1/30th, and the arrow is 20. Have a moment here. The area is 20%. So to solve this, we would multiply both sides by 30, and we would get 6. So there's a 20% probability that they'll be within the next 6 minutes. So this chunk is 20%. So find the time interval for which he is 45% likely to be late. So essentially we're doing the same thing. We're finding that 45th percentile. So we're saying 0.45 equals x times 1/30. Multiply both sides by 30, and we get 13.5. So the interval is any interval that's 13.5 minutes long. So from now to 13.5 minutes, you is how you would really kind of do that. All right, so that's the uniform curve. Now we're going to talk about the normal curve. The normal curve is a symmetrical curve. Same on both sides. If it's perfectly symmetrical, that's the normal curve. So it's also could be said normally distributed, normal probability, bell curve. All of these things are going to tell you that that's a normal curve. So the properties are that it's symmetric. It's approximately even on both sides. In this case, the mean, the median, and the mode are all this high point. So we talk about the mean when we're using a symmetrical curve, but in theory, if it's perfectly symmetrical, those are all the same. They spread out by standard deviations. So if you go up 1 standard deviation, up 2 standard deviations, up 3 standard deviations, that's how the data is spread out. And then you also go down. And that's kind of how we would draw the curves. An inflection point is where the curve kind of changes. It's just that at that deviation. So you're always going to put stars at the first standard deviation to show like, hey, I know the curve changes here. And then the area under the curve, just like the uniform one, represents your percent or probability. And there's always 2 ways to interpret. So you're going to be asked, interpret this area in 2 ways. So one way is to interpret it as a proportion. The proportion, I don't know what's going on. The proportion of people with a given characteristic is, and then you'd write the proportion, period. The other one is the probability of picking or of randomly selecting an individual with a given characteristic is, and then you write the percent. So we'll do that in a minute with like a real example. That's just what it means. So the normal curve approaches the horizontal axis. It gets closer and closer and closer, but it never actually touches. And then we use what's called the empirical rule. So this is empirical with the normal curve, not the same as empirical probability. But it's saying if we have the mean in the middle, it's spread out, the data is spread out pretty consistently. So within 1 standard deviation, you have 68% of the data. So if you cut that in half, it's 34 and 34. Within 2 standard deviations, you have 95% of the data. Oh my Lanta. So if we keep going, this is 13.5 and 13.5. And then within 3 standard deviations, you have 99.7% of the data, which would make this 2.35. And then outside of that 3 standard deviations, you have 0.15% on each side. So those percents, again, we're talking about people, so it's not perfect, but those percents can help us make predictions based on data. And then we'd put our inflection points right there. So now let's look. The relative frequency distribution given on page 360. So if you want to look in the book, you can look at it. But essentially what it's doing is it's telling you the heights of a pediatrician's 3-year-old female patients. The mean height is 38.72. So we're going to put 38.72 right here. Then our standard deviation is 3.17. So every time we go up, we add 3.17. So this becomes 41.89. This becomes 45.06. And this becomes 48.23. Then every time we go down, we subtract 3.17. So this becomes 35.55. This becomes 32.38. And this becomes 29.21. So that's our mean and standard deviations. And then when it talks about the parameters, you also want to put your stars for the inflection points. So that's the type of question you might be asked. Now let's look at another one. The serum total cholesterol for males between 20 and 29 years old is approximately normally distributed with mean 180 and standard deviation 36.2. So first, let's draw our curve. So 180 is our mean, and then we add 36.2 to 16.2, and then we add 36.2, and we add 36.2, and then we do the same thing but subtract, subtract, subtract. So we have 3 of each, and then draw our inflection points. So now we've labeled our parameters. Then we're going to answer the questions. So an individual with total cholesterol greater than 200 is considered to have high cholesterol. Shade the region to the right of x equals 200. So 200's about here, so we shade to the right. So that purple represents the proportion of people that would have greater than 200. So let's say mathematically that purple proportion adds up to 0.2903%. We're going to do the 2 interpretations. So this is back those 2 here in blue. So the first is the proportion of the population with, and then we're going to list that characteristic. So cholesterol greater than 200 is 0.2903. The other interpretation is the probability of randomly selecting an individual with a cholesterol of 200 or greater is, and then you write that as a percent, 29.03%. So that is 7.1. Let me know if you have any questions.